Hey up, this is a Blender Simulation Nodes tutorial. I'll show you how to make this cell division sim seen here. You're going to need the Simulation Nodes branch that you can download here. Once you've got it downloaded, head into Geometry Nodes. So we can delete our input geometry node, we can bring it back later. We need to have a points node and then our simulation. We need to add our output first. So now we can just connect all of these up. So we're going to take that point in, and one thing that we're going to want to do to that point is it's going to want to duplicate over time, isn't it? So we're going to take a duplicate elements node, and we're going to need a load of logic to assign when this duplicate elements node is going to work. We can make an age attribute here. If we take a fraction of that and plug that into a compare node when it is equal to 1, this means as the age parameter goes up, every time it is divisible by 1, this will output true. And we want to plug this into a switch node set to integer, and we can plug this in here for now. Set false to 1 and true to 2, and we can use this as an input for our duplicate elements node. When the age is equal to 1, we will duplicate the point. When the age isn't equal to 1, it won't duplicate. There are going to be more things that we need to add to later, so for now I'm going to frame this and just call it age is equal to 1. Okay, so we've got this parameter that's age, but it's not actually being changed over time. So what we're going to want to do is store that name. I'm going to take our age value. This is going to be a float on the point domain. And every frame when this simulation iterates, we're going to add our frame to the original with a random value. Now the ranges on this you can set yourself, but this is probably an attribute that we're going to want to use later on. So to do that, we can add an input and set that to growth. I'm going to set the maximum value here to the growth group input. Now you probably don't want to have some frames where nothing's growing. It's probably good to take this value, divide it by 2, and plug that into the minimum. And then we put an age growth parameter. And then if we come to our modifiers, we can see nothing's happening at the moment in the viewport. But if we were going to set this to a higher value, we can see that the age is growing over time and more points are appearing until obviously the simulation resets. The points are all sitting on top of each other at the moment in the same position. So we're going to need to have a way to make them move away from each other. For that we can use a little trick that I've seen in other videos, which is a merge by distance node plugged into a geometry proximity node. If you take this position value, plug it into a subtract, vector math subtract, make sure it's in the bottom slot. In the top slot, we want it on our position, which is also the source position for our geometry proximity. We want to normalize this value and scale it so we have control over it later on. This then will go into a set position node, plug that into the offset, and then what we're actually going to want to do is put this into a group. Connect up the input geometry to the set position and the merge by distance node, and set the geometry proximity to points. Connect up the distance and scale functions into the input so we can control them externally, and connect the set position to the output. So we're going to take 4 of these, connect all the geometry up together, duplicate it again, duplicate it, and connect the end to the starts. So it's going to come in here and exit out over here. We can rename this group to repulsion. We're going to need some more inputs here. We want these particles to be pushed apart when they're within each other's radius. So the distance actually needs to be set by a factor of the radius. So if we make a new input and call this one radius, this is a radius value that we're able to set externally. So into our distance function on all of our repulsion nodes, we can plug in a radius, which is the group input node version. You don't want this node in the red, you want the one in the black. And just times this radius by 2, so we get this 2r. Now we can plug this into all of our distance functions. But now we need to set the scale up, which is another thing that we're going to want to control externally. I call this repulsion scale. With this repulsion scale, we can design some levels of coarseness to the simulation, requiring less overall loops. Because we've got 12 iterations here, let's take this repulsion scale, get some more multiplier nodes. The geometry is going to come in to the bottom and then come out the top. So what we want to do is to take this repulsion scale, and on the first iteration, it's going to be 3 times as large. The second iteration is going to be 2 times as large. On the last iteration, it's going to be the value we're going to give. So we can plug the bottom multiply value into all of the bottom scales, the 2 times into the second row, and then just this repulsion scale into the last one. And we can put this in a repulsion node tree. This setup won't work when all the points are perfectly on top of each other. So one thing that we need to do in the simulation is to add noise to the simulation every step, and this can just be a very small amount. We have a scale to affect it. We need to center the noise field, so we're going to subtract 0.5, and this vector is going to be from our noise texture, and we want the color. So join this into, let's make a noise scale attribute, noise scale, and we want it to be 4D texture with the ID plugged in, so each point will have a different random noise texture assigned to it, which will change over time. So this is quite a basic setup, and we can play around with some of these values to get something we would like. One thing we probably want to do is in our initial points node is we want to plug in our group radius, so the group input radius value. Say we wanted to see some more movement in there, that's probably a bit too small. Now we can see how the points move apart from each other until they're separated. So with just this simple node tree, we've got this setup where points will move apart from each other. One problem that might be a bit difficult to see is you can see values jumping in the spreadsheet editor as the duplicate elements node will duplicate an element, and that will be next to its original position in the spreadsheet, which will then shift all of the remaining positions. So we actually need to create our own stable ID system. This is one of the most complicated parts of the node setup, but hopefully it will make sense. We're going to need a set ID node, because in this ID is we're going to set that to a named attribute that we're going to make. So we've got ID info. Obviously this value is going to need to be stored originally, so set these to integer. And the name is going to be the same. And the value is going to be added. I'm going to take a max from the attribute statistic from our ID info node. So let's take a branch off our geometry section, add in this attribute statistic node, which is added with an accumulate field, and we want to take the leading value. This duplicate index tells you if the element is one that's been duplicated. With the accumulate node, we can tell how many of these are that exist, and then this is added with the largest ID info value that existed, and then we add it with how many were created this frame. And the way that the accumulate node works, this is done iteratively per element. So the first element will start with 1 and the next element will have 2, and so on. So this is the basics for our stable ID. You can see in our spreadsheet editor, as particles are duplicated, the age value is carried across to each one. So we also need a stable age parameter. I'm going to use a switch node here. And this switch node again is going to be determined by this duplicate index function from our elements. And if it is a duplicate, which will be true, we want the age to be set to 0. And if it's false, we can just use the age that already exists, because that means it isn't a duplicate. So this gives us our stable age node. Link off our duplicate index input and plug that into the selection of the ID so we don't update old IDs. And now we can see our age over time is individual for every index. Our ID is keeping track of which point in space is which ID and not the index. We're going to add a set position node And before that, we're going to have a for named attribute node. This attribute we're going to be using is velocity. And this is going to be a vector. All the way over here, you have a sample index node based off the geometry from the start of the frame. And the sample index node is going to be sampling a vector, which is actually going to be the position at the start of the frame. And we want that just to be based off the ID. So we want to find the distance between our original position and the position at the end of the frame. So we're going to subtract those two to find the difference between them. We can then put a scale in, and this is just for artistic control. And we want to add that to another scaled version of a named attribute, which is our velocity. So we've got two places here where we can control the scale of the velocity. This is a dampening scale, so we can have a velocity dampening and a velocity scale attribute. So velocity scale and velocity dampening. This add node here just needs to be plugged into our velocity, and that's for our store named attribute. And then this scale here is actually passed along to the offset. This will just help particles stay moving in the same direction, more or less. And these values might take a bit of a playing around to get sort of effect you want. So here between the noise and the repulsion, we're going to want to add in some new information. And also let's just move this out of the way so we can see properly. So after this noise, we're going to want a sample index. And this isn't actually going to be off this geometry. This is going to be off our input geometry from the group input. We're going to be looking at the index of our geometry that's been sorted through our point cloud processor. And we're actually looking for a vector here. This vector is obviously going to be the position. And this is quite similar to how the repulsion works, but in a bit of a different way. We find out how far point in our current simulation, and we find their distance to their index in the point cloud. So each point has a sort of its reference index that it will be the same as that it will be trying to get to. So the ID of 0 in our simulation will be aiming to get to the point cloud's index of 0 as well. And to find this vector, we need to subtract from our original position. And then we can scale this, some artistic control, and I call this PC attraction scale. So we've got PC attraction scale for point cloud attraction scale. You don't know what that means. And then this vector needs to go into a set position node. It's actually going to into its offset there. And that's our PC attraction node. And we just need to replace this link here. Oh, we can see we haven't actually plugged in our geometry into our set position node. We're going to need a concept of an active particle and an inactive particle. When a particle reaches the destination we want it to get it to, we want some things to shut off in the simulation for acting on that particle. We don't want it to move to a new spot. We kind of want it just to stay there. So we're going to use this active attribute. This is going to be a Boolean attribute. We're going to use a switch node to control this, which is a Boolean switch. We can just use true and false here. We're going to compare it and see if it's not equal to the position. Plug that into B, because we want the nodes to be active when they're not equal and inactive when they're equal. And the distance we're going to use to decide if they're close enough. You could kind of use anything, but I've found to help the simulation get along and not bog down too much with too many active particles, it's good to use 2 times the radius. So we're just going to multiply our input radius from the group input radius, and that. Now you can see we've got this active value, but we're not actually using it anywhere. So we want to get a named attribute, and there's lots of places that we're going to need, and we can set that to a Boolean type. So right at the start, first of all, we need to flesh out some logic here behind the duplicates elements node. We grab an attribute statistic node and take this geometry right from the beginning of the frame, and we're looking for this active attribute. So we can plug this into a map range, and we will go from 0 to the maximum of the new input that we're going to need, and this is going to be called active particle limit. Now input the active particle limit into the maximum. We can set this to smooth step, and that is going to go into a probability. So this allows us to limit on the number of particles allowed in the simulation at once. If this is set to a maximum of 2 particles, we want this probability. So if we use the subtract node, we can use some Boolean logic to say that when it approaches this, we don't want this age value to grow the particles anymore. So if we look at our simulation, we get to 2 particles and it stops. Another step of logic we're going to need to introduce here is a point cloud limit. If we're wanting to grow into a point cloud or into a mesh or something, once it's filled in all of the indexes available for it to grow into, we don't want it to continue growing because it's got no information about where to go to. So we can take a link from this original and plug that into a domain size. We're not actually going to use the integer because this epsilon from the float can go higher than 1. So that's actually quite useful. In a single simulation step, we might happen to go over the number, so we're actually just going to use 2 point clouds. From the start of the frame, we're looking at how many points there are, and we're comparing that against our group input geometry, and we can use this group input divided by 10. So if point within 10% of the size of the finished point cloud, then we will stop duplicating our points. That's the same node tree, just tidied up a little bit, so it's more understandable. And I'll take you through the rest of the tree, adding the final bits of information that will need this to work. We've got the stable age thing here, but it doesn't actually work for active particles, so we're going to need the exact same bit of logic, but just duplicated for active particles. So we bring this down here, use the same duplicate index for our switch. However, this is going to be set to a float, just because we don't have control over what's true and false with the Boolean, and we want true actually to be set to 0. So we can add this into this chain, and this can be called stable active. Now let me just rearrange this area to make this more legible. Another bit of logic that we need to add in here is just the color information, and we can use some inherencies of how this is functioning to help that work. Our color value on our point clouds is probably going to be called col, so we use that. And we can actually use a mix node. That's something like 0.7, but you can choose that value. So we're going to mix between the color that we already are, and here we're going to use the geometry of the point cloud, which is the geometry from the group input node, and we want to be looking at the color, and this will also be called col. We want to look at the ID of the colour. And then this will be mixed with our original colour every frame. So there'll be a slow change in the colour over time. Duplicate particles have the same colour and then they'll slowly fade into the colour that they're all meant to be. You can obviously adjust this factor here, but we've got so much control in the modifier stack, I thought I'd keep it simple. Then we've got our noise, our PC attraction, our active distance, the repulsion to push them apart, age growth, and then the very last bits of logic that we need to add in. We have a geometry switch, the current data plugged into false, and this coming all from the start, we can plug into true, and this just can be a way to deactivate the simulation at any point in time. So we're going to compare the frame with another custom attribute, and this one will be called stop frame. So if the current frame greater than the stop frame, then we want to stop it. We also need to make sure that if we set it to 0, if we don't want to use it, that if the stop frame is not equal to 0, that's also something that needs to be true to switch over to the old geometry. So even our stop frame is currently 0, it's still working, but if we set that stop frame to 1, then it will completely stop working. Since the age is increasing by unknown amounts, if we set this epsilon value to half of the growth value, we should hopefully catch only one instance of a growth event. This active element needs putting in some more places. It needs to go inside this here, so we need a named attribute active. This basically means that this operation will only function on active objects. And same with PC attraction. We need a named attribute with active in it. Same with noise, named attribute with active. The same with age growth, we need an active input. At the moment, I can't find a way to sort the index of our base point cloud. So currently what I'm doing is I've got some simple Python code that will sort our point cloud based off a defined center that we supply it. It will then rewrite our point cloud to a new point cloud. So basically we've got a input here that we need to write and an output here that we need to write, and here we have the center of the point cloud. So I'll show you the workflow that I use to define these. I'm going to navigate to where I store my point clouds and choose one that we're going to edit. So I'm going to pick this point cloud and open it in Cloud Compare. So in Cloud Compare, we'll simply be able to find a starting point for the center. And here at the top, we can see that Cloud Compare is a point picking tool. So we can use that, click on a point, and it will give us information about that point. We can zoom out, check that it's in the right position. I think I actually want this one to go a bit further back here. And we can see that it just gives us here listed out our coordinates. So we've got this open in idle, which is my Python IDE. Got Sarah carving the new coordinates and the output file, and we can just run this. So now that's complete, we've got our new file. Come back into Blender. With the new experimental ply importer, we can import that new point cloud. You want to use sRGB. So now it's imported, we can convert it into a point cloud and just arrange it. And then we can add our geometry nodes modifier and start setting up our attributes. The first parameter you need to set up is the radius value. The radius value of your points needs to be small enough to allow them to get to their location. If there are too many points too large around it, it will struggle. So make your points quite small. I'm also going to want to set the origin. So we're going to go object, set origin, origin's 3D cursor, and I just sort of eyeballed that. From here it's shading and rendering, and be careful with large point clouds, as it can take quite a lot of time. Thanks for watching. Cheers.